Okay guys, so this is thin layer and then gas chromatography. We'll do thin layer first. And basically, thin layer chromatography separates out different components of a mixture. And from that, you can kind of tell what the mixture is. It's not perfect. I certainly don't rate it as high as spectroscopy, like NMR, IR or mass spec, but it is cheap and easy basically to do. It's the kind of thing you could do in your college lab. Whereas you'd be bloody lucky if you had an NMR machine in your college lab. So basically, it's really simple the way it works. All we do is we take a special piece of kind of like paper, looks a bit like paper. It's called a TLC plate. TLC just stands for thin layer chromatography. And what we do is a few centimeters from the bottom of the plate, we draw a line. And we draw that line in pencil, not in pen. As I explain this, you can be thinking about why that is. And then what we do is we take our sample, usually it's a mixture, our sample, and we put that somewhere on the line. So let's say my sample is a mixture of two different components. It doesn't matter what those components are, let's just call them red and blue. So you can imagine these colours representing just two different molecules. So my mixture, we just put a spot of my mixture on the line, and then we dip our TLC plate in a suitable solvent. And when we do that, you've got to make sure the solvent doesn't come up to the line, because if it does, it'll wash your sample off and everything will go wrong. So if your pencil line's 2 centimeters up, fill this 1 centimeter with solvent or something like that. And then kind of the way it works, like I say, it's dead simple. All we do is the solvent, and there's lots of different solvents you can choose. You could use water. Generally, other things work better. But no matter what the solvent is, it will start to soak up the paper. So for the sake of convenience, let's say we did use water as a solvent. So as my water molecules are soaking up the paper, what they're going to do is they're going to latch onto my two different components in my mixture. But each of these components is going to have a different affinity for the water or whatever solvent you use. So by affinity, what I mean is they like making forces with it, whatever those forces are. Could be hydrogen bonds, could be permanent dipoles, it doesn't matter. But different components will have different affinities. So let's say my red component has a very strong affinity for the water. It's going to make lots of forces with the water, and it's going to be connected to the water quite often because it has a strong affinity for it. So as the water soaks up, my red component is going to get pulled with the water because it's making these forces with it. So imagine my top hand's the water, the red component is going to get dragged with the water as it soaks up. So as my red component has a strong affinity, it's going to get pulled up quite a large distance. And you find what happens is it also gets spread out. Now, let's say my blue component does not have as large an affinity for the water. That means it's not going to get pulled up quite as high because the water isn't binding to it as often. With the red component, as it has a strong affinity, the water latches on, doesn't really let go, and pulls it up really high. With my blue component, which we're saying has less of an affinity, my water will latch on, pull it up a bit, let go, latch on, pull it up a bit, let go. So over time, it gets pulled up much less. So let's say that ends up there. So what we have now done is we have separated my two components of my mixture. Also what you'll end up with is something called the solvent front. And that's basically how high up your solvent has gone up the plate, has dissolved up the plate. So let's say my water or whatever solvent we're using ended up this high. This would be called my solvent front. And the solvent front is just the distance from this starting line here to wherever your solvent ended up. And you'll know where that is because as up to here will be wet, it'll be a slightly darker colour than this top bit here, which is dry. So you can easily just mark that off again with a pencil. So to go back to my earlier question, why do we use a pencil and not a pen? If you've been thinking about that, the reason we don't use a pen is pens have lots of different components in the ink. So if I did use an ink pen, it would smudge loads of different colours up here and it would ruin our TLC plate. By using a pencil, the pencil stays in that place. It does not get pulled up by the water. Okay? What we also measure is what we call the spot front. And the spot front is the distance, again, from this pencil line to the top of the spot. Not to the middle, not to the bottom. We always measure it to the top of the spot. So here's one of my spot fronts. And here would be the second spot front for my two different components. What I can then do is I can measure something called the RF value. Capital R subscript F just stands for relative front. And your relative front is the spot front over the solvent front. And have a think about what number your RF value must always be less than. Your RF value can never be higher than a certain number. So think about the equation and think about what that number is. Maybe stop the video, spend a minute trying to figure it out, and then start it again when you think you've got an answer and you can check whether you've got it right. So the answer is, it must always be less than 1, because your solvent front will always be higher than your spot front. I suppose, strictly speaking, your spot front could be at your solvent front, in which case your RF value would be exactly 1, but realistically that never ever happens. So this number here will always be less than that number there. So your RF value will be less than 1. If you do this in an exam and you end up with an RF value greater than 1, what you've done is you've got these two the wrong way around. And that's a really common mistake. So you can use that as like a little bit of a safety net. If it's greater than 1, switch these two over, you've done it wrong. And what else was I going to say about that? All we can then do is take this RF value, look up a big book of data, it's probably on the internet now, and compare it. So let's say I think this red component is butanone. I measure the RF value, look up the RF value of butanone in a big book or a database and see if it matches. If it does match, I have the correct molecule. If it doesn't, then I probably don't. Also, one of the things about this is it's not the most accurate method, so it wouldn't have to match completely. RF values do change depending on loads of things. For example, the temperature, that can change it, and also, very much so, the solvent we use. So if you use a different solvent, that will give you a different RF value, because your compound will have different affinities to different solvents. So you've got to make sure you check against the right solvent. So in terms of like kind of exams kind of stuff, things you'll need to know for an exam, there's 3 really common things they always ask you about. And that is, for thin layer chromatography, what is the mobile phase, what is the stationary phase, and how do we separate our components? What physical property is it? So the mobile phase just means solid, liquid or gas. And the mobile phase means at which phase is your component moving in. Well, your component is moving when it's latched on to the water, and your water is a liquid. So your component is moving when it is in the liquid phase. So the mobile phase is liquid. When is your component stationary? Well, it's stationary when it's stuck to the solid piece of the TLC plate. So the stationary phase would be a solid. Okay? It's still when it's stuck to the solid, it's moving when it's stuck to the water, which is a liquid. So how are these separated? Now, I guess strictly speaking, you could say these are separated by their solubility in water, but the way the exam always seems to do on the mark scheme is by thinking about the stationary phase. So if they ask you how is something separated, always just think about the stationary phase. And before I can answer that, I need to go through a word, and the word is ad with a D, adsorption. So absorption is like when a sponge soaks up water. So that's when something goes inside something. So here's my sponge, here's the water, that's absorption. with a D, adsorption is when something sticks to the surface of something. So if you sit on a chair, I guess you could say you're adsorbed to the chair because you're stuck on the surface. So what's happening here is your component is stuck to the surface of the TLC plate. And depending on how long it stays stuck to the surface, on how much it adsorbs to that surface, that tells you how far up it'll move.